talk in this session. We have Professor Ara Basmajian, also from the City University of New York. I understand he's the chair now. And he will speak on counting reciprocal and low-lying geodesics in the modular group. Professor Ara, please.
Thank you. And thank you for the invitation. And this is really a pleasure. And I'm sorry that we can't be there to celebrate Ravi's 80th birthday, but we are celebrating Ravi's 80th birthday right here. I've known Ravi for quite a long time. I was thinking about how long I know Ravi, and that I know him long enough that I can't remember how long. I think one of the early times, well, I know that one of the early times I met him was at the Graduate Center. And when I would come as a student, I was a student at the time at Stony Brook, and I would come by, and there was a wonderful cohort of faculty that were very welcoming to young graduate students and everyone. And Ravi was one of those people. So it was really a pleasure to know him over the years and interact with him both mathematically and personally. So thank you and happy birthday, Ravi. And the other thing I want to say is that I'm speaking about something I don't usually, this is, I'm going to speak about more or less combinatorial counting problems involving the modular group. And I know that Ravi's done some work. Ravi's done some work in just about every field as I was looking through his papers over the last week or so. And modular group is one of them. So here we go. So this is about geodesics in the modular group. And here's a picture of the modular surface. It's the quotient of the hyperbolic plane modded out by PSL2Z. So let me describe the modular group first. I can't quite fit, I'm trying to figure out a way to fit this, sorry.
Ara, Dani just spoke about it.
Earlier, yes, I saw the abstract.
So you can skip some of this material if you like.
Okay, thank you. Yes, yeah, I'm sorry, Danny, that I think it was 4:30 in the morning here.
I understand.
Yeah. So let me just quickly though, the modular group then is the group generated by Z gets mapped to -1 over Z, and Z gets mapped to Z plus 1. It in its action on the upper half plane, it acts properly discontinuous as a discrete group of isometry, as a group of isometries. And here's a fundamental domain for the action. This side gets mapped to this side gets mapped to this side. So the picture that you see up here is the quotient. So by the way, let me back up. If we write these elements, Z gets mapped to -1 over Z, and Z gets mapped to Z plus 1, the group generated by those two is exactly PSL2Z, the modular group. And as a group, abstractly, it's Z2 star Z3, the free product of Z2 and Z3. And that's going to be relevant for us. I'm going to look at natural generators later, and the generator of Z2 is going to be called A, and the generator of Z3 B, the natural generators. So when you, back to this picture, when you glue this side to this side, this is an order 2 cone point, and then this side gets mapped to this side, and this is an order 3 cone point, and then you have the cusp at infinity. So this is the same as taking this triangle with angles pi over 2, pi over 3, and angle 0 up here, and gluing it together, what you get is the modular surface. So if you cut along the plane of the blackboard or the iPad in this case, what you'll see is here's the one triangle, and there's a copy of it on the other side. And in other words, if you go, here's the cone point of order 2, and if you go around here once, you've traveled an angle pi, and if you travel around the order 3 once, you've gone an angle 2 pi over 3. So these are cone points, and this is off at infinity in the hyperbolic geometry, this is infinitely far away, and this cusp is exponentially shrinking. Okay. So a reciprocal geodesic is one that starts in the cone point of order 2, comes back to it, and then retraces its steps. That's why I have the double arrows here. So it begins and ends at the order 2 cone point, traversing the image twice. So that's a definition of a reciprocal geodesic. There's lots of closed geodesics on this surface. This is, you could think of this as sort of a degenerate closed geodesic, because if you took, let me just draw a cartoon picture. Here's the order 2, here's the order 3. Whoops, let me do it with this. Here's the order 2, here's the order 3. And if we looked at, say, any geodesic that sort of winds around the order 2, the most efficient way, any curve that winds around the order 2, the most efficient way to get around it is really to go into it and come back. So it's sort of a degenerate closed geodesic. And so reciprocal geodesics are like degenerate closed geodesics. So that's one ingredient of what I'm going to talk about. And another ingredient is I want to talk about low-lying geodesics. So you can consider a compact exhaustion of the modular surface by cutting it off at a certain point. In this case, I'm calling the SM the compact subsurface of the modular surface given by, well, as you move out this way, there's this horocycle foliation by horocycles. And if you cut off by the horocycle of length 2 over m plus 1, m is any number. Well, let's take it to be an integer. M is any integer bigger than or equal to 1. Then you can cut that off, and that gives us this compact subsurface SM, and the SMs give a compact exhaustion of the full modular surface. When m is 1, by the way, then you've cut off exactly the horocycle of length 1, and that is over here somewhere, and you're looking at this thing. Okay, you know, by the way, that that always there's a horocycle of length 1 or less on the modular surface. Okay, so if you have a closed geodesic, we say that it's M low-lying if it's inside SM. Okay, if it stays in SM. So of course, there's lots of closed geodesics on this surface, and they go arbitrarily far out. There's always a closed geodesic that goes outside of SM. But if you look at focus on just a set of closed geodesics that stay in SM, then we call them M low-lying. And the choice of this number versus some other number is just a matter of convenience for what I'm going to calculate later. Question? Are we
All
okay?
right, I think there was a internet issue, so for a few seconds we couldn't hear you, but it's all right now.
You okay?
Yeah.
Did everybody hear about the definition of M low line?
Yes.
Okay.
Yes.
Okay. 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 It's hard. I don't. Yeah. These talks are always strange because I don't see anyone.
I know.
Okay. So here's the counting problem. There's numerous counting problems we could talk about. So determining the growth rate of various classes of geodesics as length gets larger, okay? And so what are the various classes? That's what I want to tell you about now, and that I want to consider. And what are the various notions of length? Well, there's two natural notions of length. There's the geometric length coming from the hyperbolic geometry of a geodesic. And there's also the combinatorial length, which put another way is the word length of the element of the group PSO2Z that represents the geodesic. So let me focus on geometric length. There's lots and lots of work, and I couldn't dare to give it service to talk about all of the history. It would take at least one lecture just to talk about the history or mention the history. Let me just say, starting with Huber, the set of all closed geodesics grows like, if you look at the set of closed geodesics of length less than L, then that number is grows like e to the L over L. So that's geometric growth for closed geodesics. And that occurs here also for the closed geodesics in the modular surface. But then you can ask more nuanced questions, ranging everything from that statement I just said about Huber's result to there's lots of recent work of Mirzakhani, recent meaning the last 15 years, 10 years, Mirzakhani's work on length of simple closed geodesics on a surface, hyperbolic surface, and so on. There's Erlandson, Soto, and various others that have talked about geometric growth, geometric length, and the growth. So I got interested in this in the modular group and lengths on the modular group when I was looking at a paper of Sarnak that goes back to about 2000. It's 2007. So he was interested in reciprocal geodesics, the primitive reciprocal geodesics. So that means that you do one traversal. So primitive, yeah. So yeah, maybe this is confusing. The reciprocal geodesic was, remember, you started in the comb pointer of order 2, you come back to the comb pointer of order 2, and then you traverse again. Okay, that's a reciprocal geodesic, and that's primitive. Okay, now it could be that you went along that reciprocal geodesic, you came back, that's one orbit, and then you did it again. Now, if you did it again, then that geodesic is not primitive. It's a second power of the reciprocal geodesic. So Sarnak proved that, and I'm stating it in terms of traces, but you could state it in terms of lengths of closed geodesics. So this is a hyperbolic geometry result. He proved that if you look at the set of primitive reciprocal geodesics, whose traces, absolute traces, okay, so this is the absolute value of the trace of gamma, which are less than t, are asymptotic to 3/8 t, okay? And then there's this compatible result that's much more recent, Bourgain and Kantorovich looked at, well, let's not focus on this word just yet, the M low-lying reciprocal geodesics, and the trace of those being less than t, they grow, well, at least like t to the 1 minus epsilon. Okay, so this m is a function of epsilon, and as epsilon goes to 0, the m goes to infinity, and these m low-lying reciprocal geodesics converge as a set to the reciprocal geodesics, and this is the rate at which, well, they converge quite fast at this rate, because this is linear in t, and then this is approaching linear in t. So just as a reminder, the trace, the absolute trace of an element gamma is, how do you get it? Well, you have an element gamma, a closed geodesic gamma. This is true for any closed geodesic on the surface. It corresponds to a conjugacy class of hyperbolic elements in PSL2Z, and you can compute either their geometric length or their absolute trace. They're related by this. And that's what I'm talking about here. So I got interested in this question here because I looked at the proof, and the proof was strictly number theoretic. Although I'm sure it's very interesting, I didn't understand it. So I wanted a geometric proof, and there is a geometric proof now, and that was proven very recently. There's a preprint by Erlandson and Soto that give a geometric proof of these two theorems, which were originally proven using number theory. But what happened, so this is where the story began when I was thinking about this with Rob Suzzi Valli. We sort of morphed the problem into a problem about growth in groups and word length. So we asked, we started considering a combinatorial analog or a word length analog of this growth question. So let me just set that up. So the group, so I'm denoting by G as PSL2Z. I'm going to use G instead of PSL2Z, but G is always PSL2Z for this discussion. So G is isomorphic to, as we said above, the free product of Z2 and Z3. And let me just take as the generator for Z2, the natural generator. So A, this is the order 2 element, and B, order 3 element. And if we have a closed geodesic on the surface S, on the modular surface, let's define its word length with respect to these generators. So in terms of these generators, as the minimum length in the conjugacy class of all the lifts of gamma to PSL2Z. So you have gamma, it's a closed geodesic. It could be a reciprocal geodesic. You lift it upstairs. It corresponds to a conjugacy class of hyperbolic elements. They have the conjugacy class, each of the hyperbolic elements have a word length, and there's a minimal length one. And that's what I'm calling the word length of the element gamma. So here we go. I'll state the theorem, and then I'll round back and explain. Can you see down to, I can't quite fit the whole thing on the page, so maybe I'll do this. So here's the first 2 items. So let me explain. So we're considering here primitive reciprocal geodesics. This is now word length, whose word length is less than 2t. The reason for the 2 is that word length is always even. for these geodesics. I'll explain why in a moment when I draw when I write down some of the basics. But if we look at the primitive reciprocal geodesics on the modular surface, whose word length is less than t, the number of them grow like or asymptotic to 2 to the t over 2. And this symbol means the greatest integer less than or equal to t over 2. So by the way, I mean, when I say grows like, this is really asymptotic. So the ratio goes to 1. Okay, I mean, that was what we were really seeking here, because there's lots of rough statements you could make, but we wanted to nail down exactly what the asymptotic growth rate is, and also what the constant is if there's some ratio approaching constant. So in this case, it's 1. Then we looked at the M low-lying primitive reciprocal geodesics, whose word length is less than 2t again, and that grows like this number. So let me explain. So ignore for the moment exactly what this constant is. The important thing is the constant depends on m. Remember, we're looking at m low-lying. And this base here, alpha m, that's the unique positive root of this polynomial. In particular, alpha m is between this number and this number. So notice that this gives exactly the analog of what happened up here. In the geometric setting up here, remember what happened is that when we looked at the M low-lying reciprocal geodesics, as m goes to infinity, this epsilon goes to 0, and this converges to linear. And these sets converge to exactly the primitive reciprocal geodesics. So we're essentially giving a combinatorial analog, even though I've buried the notion of fundamental. Fundamental is an algebraic notion, and which I can just mention, but it wasn't sort of relevant for the word length problem. So here you see that as m goes to infinity, these asymptotic growth functions converge to this asymptotic growth function. Let's just check this. As m goes to infinity, alpha m goes to 2. So this goes to 2, which is here. And then you do a quick computation for this, and as it turns out, this goes to 1 as m goes to infinity, based on this lower bound. So those are the first two items, and these are counting problems. And let me emphasize, there's nothing deep machinery that we're about to use. The harder problem was just making sure we get to the right framework to count. And once you're in the right framework, there's tools available to count. So so those are the first two items. And then let me just say, we also have that when you look at the M low-lying closed geodesics of word length less than 2t, this is a much harder problem to count. Whoops, oh boy. I don't know why it does that. Computing the growth rate, the asymptotic growth rate of this is much harder, just like, where are we? Just like they got a lower bound and not the exact growth rate here for the reciprocal low line here. This is a harder problem to compute. the growth rate of the M low-lying ones, where you don't assume it's a reciprocal geodesic, just all closed geodesics that are trapped in that compact subsurface SM. So what we did do is got a lower bound on the growth, and this lower bound, again, we expect that as M goes to infinity, that this growth rate converges to this growth rate, and that's what we get, obviously, as M goes to infinity. This goes to 2 to the T over T, so it's off by a constant, but that's to be expected because this isn't nailing things on the head anyway. Are there questions before I give you the ingredients of give you the sort of the ideas of the proofs?
Now, how does that polynomial arise? I mean,
Yeah. So I'll mention that just when I talk about the proofs. Good. That's good. But the short answer is it comes from a recursion relation, a linear recursion relation. And then there's sort of a natural polynomial associated to the linear recursion, and the certain roots of that linear of that polynomial give you the growth rate. It's sort of like Fibonacci. I mean, it's actually, it is that. It's sort of a generalization of the Fibonacci sequence. It's how you compute the growth rate.
linear relation involving M terms, roughly?
Yes, exactly. Yeah. So I'm coming to that. So what are the ingredients? So again, G is PSL2Z, S is the modular surface, the quotient. So just a couple of quick facts, and I'm sorry, I apologize if Dami already mentioned any of these. G is comprised of, there's only one conjugacy class of order 2. That's the one that comes from that natural generator A. There's only one conjugacy class of order 3. And there's only one conjugacy class of parabolic elements, conjugate to this. And then all the other elements and all the other conjugacy classes are hyperbolic elements, coming from hyperbolic elements. So, and closed geodesics, including reciprocal geodesics, correspond to conjugacy classes of hyperbolic elements. So let's think about this. If you remember, our generators are the order 2 and the order 3 for the group G. And if we want a conjugacy class representative of gamma, right, you lift upstairs, you have all these hyperbolic elements. And well, they're given by a word in these generators, A and B. And now if you think about this, you could always conjugate so that you get a word that looks like this. You could always conjugate so that the word starts with A, ends with B, and it's of this form. It's A, B, epsilon 1 up to epsilon T, where the epsilon I are plus or minus 1. Right, because B has order 2. So I could think of the power here being, so powers of B are either plus 1 or minus 1, or either plus 1 or minus 1. And
B has order 3 or?
B has order 3.
The order of B is 3. Is that what you're saying? Yeah. So B is order 3, and then there's no power of A because A is order 2. So and if you had a word that started with say B, for instance, and ended with B, well, you could always conjugate so that conjugate this to this side, because you could cyclically rotate, permute, and that corresponds to conjugation, and then you'd get something that starts with A. So you could always start with A, and then similarly, you could always arrange to end with B. So all the conjugacy classes are represented by words that look like this in PSL2Z, with just a few minor exceptions, namely this element A, this element B, and well, I guess that's it, a B or B inverse. Aside from these three elements, every other element looks like this. Okay, sorry, every other element is conjugate to something that looks like this. So that's the first thing to say. So now we've translated the problem. So yeah, let me back up a moment again. Let me stay focused on this. So what's the word length of this, if we had some G, we had some G in G, well, you have lots of choices in the conjugacy class, and the word length is the minimal length word in the conjugacy class, okay? And as it turns out, when you write like this, starting with A and ending with B, a representative of the conjugacy class like this already realizes the minimal length word. So this has length. I'm using T here to denote length. This has length. Well, there's TAs, and then there's T of these epsilons, and the epsilons are plus or minus 1. So altogether, this has length 2T. And so all the conjugacy classes are even length. That's why above, when we were looking at growth rates, we were looking at words of length 2T. So now let me go over to reciprocal geodesics. How do you write them as a word? Well, let me focus on this picture. If you had a reciprocal geodesic, remember we said it starts in an order 2. So I'm looking at a lift of a reciprocal geodesic. Here's a lift. It's the axis of a hyperbolic element. The reciprocal geodesic starts in the order 2, goes along, hits the order 2, remember downstairs, and then bounces back. Well, the reason why that we even talk about reciprocal geodesics is because this is really the same thing as saying you found an axis of a hyperbolic element that passes through one of the order 2 fixed points. And if it passes through one of the order 2 fixed points, it has to pass through another one. In fact, it passes through infinitely many, and there's a closest one. And that element, if it was primitive, will be the product of those two order 2 elements in PSL2Z. But every order, remember we said there's only one conjugacy class of order 2 element. So you can always take the axis and move it, conjugate, so that the axis of the hyperbolic element passes through the fixed point of that one of the generators, which was A, that was Z gets mapped to -1 over Z. So that's I. And then there'll be another one here. So I is so the fixed point, the element that fixes I, and that element Z gets mapped to -1 over Z, that corresponds to the element A in the abstract group Z2 star Z3. Remember, that was the order 2 element. And then this hyperbolic element is a product of these two order 2s. Here's the 1 order 2. Whoops. I don't know why it does that. Here's the 1 order 2. And then it should be the product with another order 2. But that other order 2 must be conjugate to the original A. So here's the conjugation. You're conjugating this element A by this group element. Starts with B, ends with B. And notice this is the inverse. right? So if I formally, maybe I wrote this down again in another way. Whoops, let me go back here. Yeah, let me write it over here. So this reciprocal, this hyperbolic element that corresponds to the reciprocal geodesic, I just said is equal to an order 2 times another order 2, right? Called the other order 2 H. I'll call it Y, say, okay? But the other order 2 is conjugate to A. So this is really A, H inverse. So this is really the commutator of A with H. So all reciprocal, all words that come from hyperbolic words that come from the reciprocal geodesic look like this. They're conjugate to something that looks like this. It's the commutator of A with some H in the group. And so, and then we could normalize and think of H as, H should start with B and end with B if I'm going to write it as a word. So that's how you get, this is the H part here. And this is H inverse. And here's the element A that you're conjugating. This is exactly this. Okay, and the reason why I'm writing it this way is because I want to count. And if I want to count word length, I have to write some sort of normal form. In fact, let me just step back for a moment. How do you count? Counting can be hard. And the game is always sort of, you have some set of things you want to count. Maybe in this case, it's conjugacy classes of something. So you find normal forms for the conjugacy classes, and you move everything to normal forms and you count the normal forms. But you also have to be careful, are all the normal forms distinct up to conjugation? And that's the one subtlety. But once you get normal forms, then the counting problem becomes much easier. So, so I just described, was there a question? Let me just recap what I just described. So here's the normal form for any closed geodesic when we write it as a word. Here's the normal form. Here's the normal form for a reciprocal geodesic. And now one last ingredient. What do M low-lying geodesics look like? Well, M low-lying, if you looked at the definition, meant again that you stay in this compact part, and it's a well-defined compact part. You can't go any deeper into the cusp than this height for the lift of the hyperbolic element that corresponds to that M low-lying geodesic. In particular, the way I set it up was that we cut off the modular surface. This is SM. We cut off the modular surface at the horizontal length, what was it, 2 over m plus 1. So that happens when you lift any geodesic. Now, if you lift any geodesic, closed geodesic that's in here, then its lift has to stay below this height here, m plus 1 over 2i. So the height m plus 1 over 2, because if you went further into here, you're outside of this compact part. So hence the name low-lying. Stay below the cusp of this height. So how does that translate in terms of the word? Well, you see, if you go into the cusp, the height of this axis of the closed geodesic from downstairs is exactly measured by how much you wind around the cusp. And winding around the cusp is exactly has to do with these powers appearing with the same sign consecutively. So each one of these, AB epsilon 1, AB epsilon 2, up to AB epsilon t, these are parabolic elements. They're all conjugate to each other, but they're parabolic elements. And see, if you had AB, 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 so in other words, the same sign epsilons, then what you're doing is you're doing that parabolic element to some power, which means on the surface, what you're doing is you're winding around the cusp to that power. And again, the more you wind around, the deeper you go into the cusp. So there's going to be a bound on how consecutively you'll see the same signs. So that's what this statement is. And in fact, it's exactly to stay in the M, to be M low lying, you could only have at most M consecutive epsilon i's having the same sign. So this is the geometric part of the discussion. The last geometric part. This is what I was just explaining here. And so let me give you like a cartoon of what's going on. And I'll finish with this. So there's a lot of information packed here. So let me start over here. So I just want to give you the flavor of the counting problems involved. So these are the various classes of geodesics that we're considering. So geodesics of length less than, so I'm not taking less than right now, I'm taking equal to, it's just easier to write things down. So these are the geodesics of length exactly 2t. Here's their normal form we just described. And for your amusement, this corresponds to the necklace problem. So the necklace problem is you have two colors of beads and you have T beads, and the question is how many necklaces can you make with those T beads, where of course two necklaces are the same if you could cyclically permute one into the other. So that problem is this counting problem is exactly this problem. Counting the geodesics of length equal to 2t, and that the growth rate is exactly asymptotic to 2 to the t over t. You could see why. Look over here, you have two choices at every stage of colors, but then since cyclic permutation means that you have the same element, the same necklace or the same geodesic, then you divide by well, the number of elements you have, which is t. This isn't quite right. You have to argue a little more because this is what happens generically, and generically is good enough because they dominate the ones, because it is possible to have a cyclic permutation that's less than length t of the necklace, and then you repeat the same picture again, they're equivalent. But that happens, that corresponds to non-primitive elements in here. So it doesn't happen very often. And the number of them goes to 0 as t goes to infinity. This is because of the presence of exponential growth. So that's what's happening here. And then there's the analog over here for M low-lying geodesics that are length 2t. And then here's the normal form, what we just said. And then that corresponds to a necklace problem, where now you've asked a more subtle question for the necklace problem, because at most M consecutive beads can be the same color. That turns out to be a hard problem. And I don't know what the asymptotic is for that. And looking at the literature, there's lots of things written about this or equivalent to this question. But to get an asymptotic formula, you need to, you need a closed form for this, so to take a limit as t goes to infinity. And most of what all of what I've seen in the literature are open form. They're written as sums. So you can't take a limit. The sum gets goes off, the size of the terms go off to infinity. So this is the best we could do on this. And then so on. And let me go down to, these are the reciprocal geodesics, and they corresponded to these. And then that corresponds to what are called compositions. So now we're changing our point of view slightly. So this is a combinatorial property or number theoretic property. You start with T and you look at the number of sequences of positive integers that sum to T. Okay, the number of possible ones. So this is not, so it's not a partition because order matters. Because order mattered in these epsilons here. So order matters here. So that's why it's called a composition and not a partition of T. And you count the number of partitions, and it turns out for reciprocal geodesics of length 4T, all reciprocal geodesics are multiples of, the word length is multiple of 4. They grow, well, they're not grow, they're equal to 2 to the T minus 1. And then this last one, and I'll finish with this, the reciprocal geodesics that are M low-lying, this we mentioned already, there's the normal form. They correspond to a much more complicated thing, these compositions of T, where the terms are bounded by M. That corresponds to this M of these not being consecutive to the same sign. If we call this CTM, right, this set, then its size can be written down recursively like this. This is a linear recursion relation. It's sometimes called the generalized Fibonacci relation, right? So this means the elements that sequences of positive integers that add up to T, but none of the parts, none of the terms of the sequence go above M. So this is the number of these, and you get this linear relation by just, well, it gives you a recursion relation, and then that recursion relation leads to that polynomial that Ravi was asking about. And then that leads to, this is known in the literature, this was already computed as this, and this is strictly, this is an equality. This is on the nose, and that allows us to take the limit as T goes to infinity to get the asymptotic. Okay, I'll stop here. Thank you very much, and happy birthday, Ravi.
Thank you very much. It's open for questions.
Nice thing is number theory being replaced by geometry. I like that kind of.
Well, you know, we had trouble.
Counting is hard.
Counting is hard, but actually it was sort of interesting. We thought that we could do some sort of counting, and coupled with some geometry, to get to Sarnak's result, but we never got there. And then there's another idea, and that's what Erlandson and Soto did. And their proof is really geometric, and it's very elementary. The idea is very simple. They turned the problem into a lattice counting problem, and then they make it geometric, and then there's the literature is littered with looking at the set of lattice points within the distance R of a base point, and then you do that, and then you need to modify that a little bit because you're looking at reciprocal geodesics, but that's the idea, and they translated it and they made it work. So so they now have a geometric proof. I mean, again, I should say the reality is I didn't understand the number theory proof. That's Sarnak's number theory. I'd love to have somebody explain to me those ingredients.
Yeah, so I was asking, I mean, so whatever you have discussed here, so have you written them down as a preprint on the archive or somewhere?
It's on the archive. Yeah,
it's on the archive.
I mean,
Okay.
yeah, there's a new version that's gonna appear in groups geometry and dynamics
Okay.
soon. But we'll put up the latest, the version that's going to appear in the or about to appear in the paper,
Okay.
in the journal. But there is an earlier version on the archive from 2020, I believe.
Okay.
This is pandemic era math.
Yeah.
And I should say that my student Blanca Marmoleo, in her thesis, generalized, there's natural generalizations of these questions to Hecke groups. So, if you really come down, I'm couching everything in geometric language, but the reality is we're really looking at this group Z2 star Z3. And this is all about the group Z2 star Z3. And so she looked at Z2 star Zn and has results for n odd for these questions, and also Z2 star Z. Similar but different results.
What kind of number theory goes into Sarnak's proof?
I was hoping you would explain that to me.
Just curious, maybe some catchwords or whatever.
It's been so long since I looked at that. I don't even remember. I don't even.
Counting
the
rational
embarrassing
points of
thing.
varieties over finite fields or something, or
No, I don't think it's. I don't think it's that. I mean, dihedral groups are involved, but that's obvious because there's Z2 star Z2 already here. But I don't know. Yeah, I mean, the embarrassing thing is I don't even know whether the number theory that's involved is standard or or more creative.
okay. I guess if there are no further questions, let's thank Professor Basmajian once again.
Thank you.
Very interesting talk.
Thank you.